This talk about the cutaneous senses is the final part of talking about touch, our sense of touch. So we've talked about perceiving details. We're actually going to get back to perceiving details, but we're going to take this break to talk about vibrations because that's important actually for perceiving details as well in a really different way. So the Pacinian corpuscles are how we feel vibrations. If you remember me going through the mechanoreceptors and talking about the Pacinian corpuscles as giving me the feeling of my refrigerator running or the feeling my car running or whatever, or my key going brrr, brrr, that those vibrations are felt by the Pacinian corpuscles. And how we know how Pacinian corpuscles work comes from work from Werner Lowenstein back in 1960, where if we look at A, if they gave a rapid vibration, we see that the nerve ending, if you see the bare nerve ending, it is surrounded by what looks kind of like an onion, but what's in that onion-looking thing is a liquid. And so sometimes I compare this to a waterbed. If you feel vibration on a waterbed, you're going to keep feeling that. Well, that's what's happening when we feel a vibration. That liquid keeps moving and vibrating, and so that bare nerve ending is what's sensing that. Okay. So it's going to keep responding. If we have continuous pressure, just like if someone gets on your waterbed and they sit down, you're going to feel it when they sit down, but then it's going to stop, right? You're not going to feel it anymore. And so continuous pressure, if you look, we don't feel that at the bare nerve ending. We only feel it when it starts and when it stops. So when it comes on and when it goes off. And so what Lowenstein did was he pushed at A and noticed that this what the Pacinian corpuscles nerve fiber there, it responded when we started the push and when the push came off. And then he dissected this and kind of took off that surrounding area and went in and pushed at B. So pushed directly at or stimulated directly at that nerve ending, and it responded constantly to the stimulation at B. So what it's doing is it is responding to the stimulate when it is stimulated, but because of this kind of liquid around it, that it's being stimulated only when something starts and when something stops, just like when someone gets on and off your waterbed. If so, what it tells us about is vibration. And for the Pacinian corpuscles, specifically, fast vibrations. So part of telling the details of an object or perceiving the details of an object is perceiving the texture of an object. And this is where we really use both, it looks like, our Merkel receptors and our Pacinian corpuscles. And it looks like we use two different cues. And so this has been referred to more recently as the duplex theory of texture perception. And Mark Hollins has done a great deal of work on this with several colleagues. But this duplex theory of texture perception, really the crux of the theory, was proposed back in 1925 by David Katz, who suggested that we use spatial cues, so those relatively large surface elements, those bumps or grooves that we feel when the skin is moved across the surface, but also when it's pressed on to elements, okay? So when I'm pressing something onto the skin, when we saw that weird raised pattern back and we looked at the Merkel receptors, those were spatial cues, right? As we're just feeling that pattern. Sometimes what I do is I pull out a notebook, and so you might want to do that with one of your notebooks. As you feel the top of the notebook, you can feel the entire thing, the pattern of it's just smooth, right? But if you turn your notebook so that you're feeling the wire edges, you can feel how close, to some extent, how close together those wire edges are, and now you can also feel this. It's not smooth, right? Those are jagged kind of edges. So we're using those spatial cues, the bumps and grooves, but we're also using what he called temporal cues, so cues that we're using really across time, or the information about the specific vibration due to movement over the surface. And so now if you're going to take your notebook again and you want to feel across the top, there's not really much about a change over time. You're not really getting information that's changing for that temporal cue, and so you can tell that it's smooth. But if you go back to your wire, that wire binding, and move across that, you can feel again how, and you can do this with different notebooks that have different wire binding. You can start to feel based on the vibration how close together those wires are, and that it's not smooth, it's bumpy. So you're getting both of those pieces of information to tell you about the texture of an object. Okay, so for perceiving texture, this is a study by, I think it was Mark Hollins and Ryan Reisner, and they did some adaptation. So remember, we've talked about before the slowly adapting. When we are slowly adapting, what's happening there is neural fatigue, right? That's what we mean by the adaptation, as opposed to the rapidly adapting corpuscles here that are responding to on-off. That's really two different ways of talking about how these neurons are adapting, and it's a little bit confusing, but it is what it is. That's the way it's talked about. So if we look at what they were having people do in this study, is participants were running their hands over a standard texture and a test texture, and people were indicating which texture was finer. Okay, which one had finer kind of grains of sand or whatever in this case, for example. And if you notice, so if I'm comparing two and I'm saying which is finer, if I'm at 50%, I am at chance. If I'm at 50% accuracy or 50% correct, I'm at chance level. And they had a number of adaptation conditions, one where there was no adaptation. They had the first adaptation condition where the skin was vibrated at 10 vibrations per second, or 10 hertz. They did this for 6 minutes, so fatiguing those neurons. And in this case, they're fatiguing the Meissner corpuscles. So if you remember, the Meissner corpuscles are responding to something like hand grip, but they're responding to those changes, those pretty slow changes. So these slow vibrations are going to fatigue the Meissner corpuscles. In the second adaptation condition, the skin was vibrated at 250 hertz. So this more like a vibration, like a hand vibrator or your car running or something like that. And so in this case, they are fatiguing the Pacinian corpuscles. Okay, if we look at the results, so looking at the figure, if there was no adaptation, people could tell the difference between those textures. They were about a little bit over 75% accurate. If we look at the adaptation of the Meissner corpuscle, so RA1 eliminated is how that is denoted there. So sometimes Meissner corpuscles are rapidly adapting 1. Pacinian corpuscles are talked about as rapidly adapting 2. It's just their other name. So RA1 is eliminating the Meissner corpuscles or fatiguing the Meissner corpuscles, and people are just as good at telling the difference between these two textures. And if we look at the second adaptation condition where the Pacinian corpuscles were eliminated or adapted, then we see now people are at chance. So it looks like really for us to tell the difference between those textures, we are using these, what we were going to call temporal cues, or the vibrations, so that what's changing over time. And if we don't have the Pacinian corpuscles, we can't do it. It's the Pacinian corpuscles that are allowing us to feel that texture. Research on temporal cues has also found that we can sense vibrations using a tool. So if you think about running a pen over the back of your notebook, and we can sense a surface remotely by the vibrations that we feel in that tool. And basically what we're feeling, right, is the tool vibrating, and we interpret that in our brains as texture. For perceiving objects, it's good to distinguish between active touch, where we are exploring an object, usually with our fingers and hands, moving our hands around haptically, and this kind of haptic perception of three-dimensional objects as we're exploring with our hand. We do explore, as I've already said, young kids, toddlers and so forth, explore more often with their tongue, but we might explore our food with our tongue. If you've ever walked on the beach and really kind of felt the sand between your toes and felt through that, you're to some extent you are exploring the feeling of the sand. We could call it that. But usually this is with our fingers and hands. And we distinguish that from a passive touch where someone's really touching something, applying something to our skin. And we talk about these kinds of touch really differently as we're doing an active touch. We usually talk about the objectness, or that sensation is belonging to the object, Whereas with passive touch, we usually say things like, that feels sharp. We're talking about the perception and the feeling of this on our skin. I'm going to read the example from page 347. I usually have a student do this. These last chapters of the book, Touch and Pain and Taste and Smell, is where I really feel like everything got the most interactive and was the most fun in my classes, which is one of the reasons I flipped all this around and did the higher level vision later. But I'm going to have to read this, and I'm going to. This is Girat Vermage, I don't say his name right, who is blind at the age of 4 from a childhood eye disease. And he is now the Distinguished Professor of Marine Ecology and Paleoecology at UC Davis, the University of California, Davis. And he is being interviewed for Yale Graduate School Biology Department. And he's blind, so these people don't think much of him, or that they don't think he could possibly, right, succeed at Yale. So here's what happened, as told by Vermage, 1997. Here's something. Do you know what it is? Bell asked me as he handed me a specimen. My fingers and mind raced. Widely separated ribs parallel to outer lip, large aperture, low spire, glossy, ribs reflected backward. It's a harpa, I replied tentatively. It must be a harpa major. Right so far. How about this one? Inquired Bell as another fine shell changed hands. Smooth, sleek, channeled suture, narrow opening. Could be any olive. It's an olive. I'm pretty sure it's Oliva cyana, the common one from Florida, but they all look alike. Both men were momentarily speechless. They had planned this little exercise all along to call my bluff. Now that I had passed, Bell had undergone an instant metamorphosis. Beaming with enthusiasm and warmth, he promised me his full support. So again, they weren't thinking this blind guy was going to do very well in the biology department there, but showing with his haptic exploration and with his active touch that he could identify these shells. If you can imagine doing that, the specific shell. I will tell you, one of my interactive kind of, I don't want to call it a lab, but more of a demonstration, is to have a smell lab. It's really a demonstration, and at the same time a touch lab where you guys feel objects in paper bags where you can't use your eyesight, and you're trying to decide what an object is based on just touch. And I do have a couple of shells in there, and people usually say shell, and then I sometimes have someone say the whelk shell or the conch shell, and I do have an olive shell in there, and some people get that. So we can do this, and I'm going to strongly recommend again that you go do these. You go do these kind of labs or demonstrations on your own. And so have somebody put a few objects into paper bags or somewhere where you cannot see them, and just explore them with your hands and say to yourself, how am I doing this? What is my strategy and my haptic exploration, and can I tell what the objects are? And you might decide to do that. So after going through a few of these slides and maybe thinking about all of these things. So we're using pretty much all of our systems together in a cooperative kind of way in order to do this haptic exploration, as it's called. Our sensory system, so we're detecting the cutaneous senses, the touch, the temperature, the texture. Our motor system, as we're moving our fingers and hands around, and the cognitive system, that is taking in information about what's coming in from the cutaneous senses, about the sensations, and putting that together with the motor system and deciding where to move the hands next, and then how the hands move around. That kind of proprioception as well as being taken in, so that we can figure out what an object is. Susan Lederman and Roberta Klatsky have done a couple of studies looking at these exploratory procedures, or these haptic procedures, and they discovered that people tended to use a number of specific procedures. And so again, I usually try and make a pretty big deal about this, and And I usually ask a short answer question about it because we have done this lab interactive kind of experiential thing where I try to get you all to really think. Have I used, and put this on the screen as you're doing it. Am I using lateral motion? Am I moving my hand back and forth across the top of something in order to figure out the texture? Am I using pressure, okay, to figure out the shape or the buoyancy, what it feels like? Am I using enclosure, which is much more clearly about figuring out the shape? Am I putting my hand around the entire object to get an idea of the shape? And am I doing this kind of contour following where I am moving my hand around the object to figure out both aspects of the shape and really about the texture of the outside of it as well? And usually people tell me that they did try those. People give me specific examples of trying those with the different things. And I usually have stuffed animals and shells and different kinds of things in there that you are going to kind of use pressure and enclosure so that you are trying these different exploratory procedures, these different haptic procedures. And usually I have people tell me a couple of other things that they use. And one example is I have this weird, oddly shaped nut that people don't know quite what it is because it's really oddly shaped. And so people tell me that they ping it to hear it. I can't think of other things that people have said, but these are the basic haptic procedures that Liederman and Klatsky found. And so you really do want to go through and just have a few things in a bag and go through these three slides in a row here and say, how am I using these different systems together, the sensory system, cognitive system, and the motor system? How am I using these different procedures? And to remember that this is really an example of active touch. Okay, I'm going to do a little bit of the physiology, so which involves both the responses of the mechanoreceptors as well as the cortical responses in the thalamus and somatosensory, the primary somatosensory cortex, and the frontal and parietal lobes. So if we look at what's happening with the mechanoreceptors, and he gives this really nice example, and we kind of saw this with that bar with the raised pattern and how those Merkel receptors responded, that the raised patterns that were more isolated had more activity in the Merkel receptors. We see the same kind of thing, that if I have like a larger ball so that ball is touching more of my finger, we're going to have this kind of shallower slope and less overall activity of those main Merkel receptors and of all the Merkel receptors around it. But really the main ones are, we don't have the same kind of slope, and we don't have the same kind of activity in those ones that are really feeling in the center. Whereas if we have a smaller ball, that's going to be touching fewer of the Merkel receptors, and what we're going to see is this real steep slope, okay, as the Merkel receptors that are responding more strongly. Again, I know everybody really wanted to talk about receptive fields again. That is everybody's favorite topic. It's not, and I kind of beat it into the ground because it's particularly important when we're looking at touch. So if you are interested in becoming a physical therapist or any kind of thing where you're dealing with people's bodies and a sense of touch or a sense of pain, these receptive fields are really important to understand. And we see, I think, very interestingly, although lateral inhibition is the only way for a sensory system to really work, because we want to feel relative, the information that's relative to the rest of the world, not absolute information, just like I said with vision. But we see these same kind of center surround receptive fields with an excitatory center and an inhibitory surround, and he's showing that there on the monkey's arm. So as we get a small object, and we just saw this with the ball, that goes right in, hits in that excitatory center, we're going to have a lot of activity. As that object gets a little bit larger and starts hitting some of those receptive, that inhibitory surround, we're going to see less activity. And this was measured in the ventral posterior nucleus of the thalamus. So here we're seeing in the thalamus, center surround receptive fields. Does that sound familiar? That should sound familiar. Heterogeniculate nucleus. We're going to move out to the cortex, to the primary somatosensory cortex, there, S1. We still see some with center surround receptive fields. We have others that respond to more specialized stimulation. So here's a neuron that responds to, neuron 1 responds best to a horizontally oriented edge presented on the monkey's hand. So we're measuring from that area of the homunculus that's feeling the monkey's upper palm there. And one of the neurons in there is going to respond best to a horizontally oriented edge. It's not responding as we get farther and farther off of that horizontal, and it's not responding at all when we're getting to a vertical oriented edge. Does this remind you of something? This should remind you of something. That's what I have my green question, and so I am going to tell you the answer. In neuron 2, we see that this neuron responds best when so we're looking now at the monkey's tip of the finger. We have a neuron there that's in that part of the homunculus that responds best. This is the same with the palm, but just to the example, that is going to respond best to stimulation that is moving in a particular direction across the finger. So if it's going up and to the left, I'm going to feel that. I'm going to have the neural response. If it's going down and to the right, I don't have the neural response. So does this remind you of something? I'm hoping this reminds you of something. This should remind you, right, of simple cells and complex cells in the visual cortex that we talked about before, those receptive fields of what the neurons are responding to. We see really similar response in the primary somatosensory cortex. We also see in the primary somatosensory cortex in S1 neurons that are going to respond best when the monkey grasps a particular object and not as well when the monkey grabs different objects. And so in this case, we have that kind of sharp edge of a ruler, that neuron responds. And when we put something that's more rounded, like a cylinder in the monkey's paw, that neuron does not respond. And finally, also similar to vision and what we see for hearing, is that cortical neurons are affected by attention. Right? We have to be paying attention to something to have much of a conscious experience of it. So what they did with the monkey was they either had a task where the tactile information was important for the task, which is the red line, or they had the monkey, the tactile information was in the hand, but the monkey was doing some kind of visually oriented task. So the attention was to the visual task. And what we see is the red line showing us neural response. We see a high firing rate to when the monkey is actually paying attention to, for the task, the tactile information. But even though that tactile information is hitting the paw or wherever on the monkey, if the monkey is doing a visual task and not paying attention to what's happening tactilely, then we don't see so much neural response. So in the past, I've really been bad about putting summary slides. Sometimes I'd either forget or there were just questions for you all to go back, but I will have summary slides here and there now because of going online last semester. And this one goes through basically what we've talked about for touch. The mechanoreceptors, all those different sensory receptors that give us different kinds of information about the world and what we're feeling in the world with our skin, with the stretch of the skin, with the hand grip control and everything. The pathways to the brain. So I distinguished the medial lemniscal pathway from the spinothalamic pathway and really only talked about the medial lemniscal pathway very much, and then we'll talk about the spinothalamic pathway starting on Friday. The brain region, so this information all goes through the thalamus, which was what was important for this class, and then the primary somatosensory cortex, that first level of higher level cortical processing. But I will say also the secondary, so the somatosensory cortices, as we are processing that information in the cortex, and that how all of these play their roles in the perception of detail, of vibration, of texture, and then how all of those, the ability to perceive all of those things, tell us about the objects that we are feeling in the world as we are trying to figure out what we are feeling with our sense of touch.